Welcome to another presentation of historic electronic technology in the series Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am David Beams. I'm an Associate Professor Emeritus of Electrical Engineering at the University of Texas at Tyler. Today's presentation might be called A Tale of Two Centuries, because it's a story of old technology meeting new. The old technology comes from the 1950s, and the new is from the 2010s. We're going to characterize the electrical behavior of two germanium PNP transistors from the early days of solid-state electronics. And we're going to do this using a myDAQ data acquisition system manufactured by National Instruments and a curve tracer module which was designed and constructed at UT Tyler. We're going to measure the relationship of collector current to collector to emitter voltage for fixed values of base current. These are the so-called common emitter electrical characteristics of the transistor. But don't worry if you find this confusing. Common emitter characteristics will make more sense when you see them depicted in graphical form. Here is our apparatus, our experiment. The module you see here is the myDAQ. It includes 3 power supplies, plus and minus 15 volts and plus 5 volts, 2 analog inputs, 2 analog outputs, and digital timers. For this application, we will use both the plus and minus 15 volt supplies, both analog inputs, and both analog outputs. Now, this circuit board is the curve tracer. In connection with the myDAQ, it's going to produce stimuli for the device under test and will convert the device under test current into voltage. In this case, the stimuli are the collector to emitter voltage and the base current. And the device under test current we're interested in is going to be the collector current. And this little black dot up here, this is the device under test. In this case, it's a modern 2N3906 transistor. We'll look at the antique transistors shortly. And if you want to, there is a paper that's published about this curve tracer for use with the myDAQ module, which can be downloaded from this publicly available archive. This URL will appear a couple of other places in this presentation. You don't have to try to scribble it down hurriedly right at the moment. This is the schematic diagram of the curve tracer module. And yeah, makes your eyes just glaze over, doesn't it? Well, let me explain what you're seeing here. So we're going to divide it into functional blocks A, B, and C. And block A is a voltage-controlled voltage source. The voltage-controlled voltage source uses as an input a triangle wave generator that is derived from the myDAQ. And that triangle wave generator is applied to a precision half-wave rectifier, so we can choose either the positive going half or the negative going half of the triangle wave. And then that is used to drive a gain of 6 voltage amplifier. The output of that amplifier becomes the stimulus collector to emitter voltage for the device under test. Block B is a trans resistance amplifier that converts the collector current of the device under test into a voltage that's measurable by the myDAQ. The trans resistance of this amplifier is 500 ohms. That is 2 milliamperes of collector current in the transistor under test will produce an output voltage of 1 volt from the trans resistance amplifier. And block C is a base current generator which takes a DC input voltage from the myDAQ and converts it into a current that drives the base of the transistor under test. Now let's look at the myDAQ virtual instrument programs that are used with the tracer. This is the function generator, and it provides that triangle wave voltage that drives the voltage-controlled voltage source to produce the collector to emitter voltage sweep. The DC level controls the base current generator, which has a transconductance of 25 microamperes per volt. In this case, the DC level is set to minus 2.4 volts. It's providing minus 60 microamperes base current to, in this case, it's the 2N3906 PNP transistor. And this is the 2-channel oscilloscope virtual instrument. The traces here came from the 2N3906 PNP transistor, and what you're looking at here, the green trace is the collector to emitter voltage versus time. The blue trace is collector current versus time with a scaling factor of 2 milliamperes per volt. And the oscilloscope can save these data as voltages versus time. Now, from these, we can plot current versus voltage with a program like Excel. We'll simply suppress the time information. We're not interested in that. We're interested in the plot of collector current, as shown in the blue trace, versus collector to emitter voltage in the green trace. And we import the data that you see here and plot them with Excel. We get a characteristic curve like this. This is a plot of collector current versus collector to emitter voltage for the 2N3906 transistor with a base current of minus 60 microamperes. And it clearly shows saturation and active operational behavior. We can take data with other base currents and plot them on the same set of axes and produce a whole family of characteristic curves for the device under test. Now, for the complete details of the tracer and its use, here again is that URL, and I will pause for a few moments, give you a chance to either stop the video and write it down, or maybe write it down in a hurry. And now let's go. So now let's go on to measuring a real antique. This is the CK722 as the device under test. And its connections are the emitter, base, collector. And the case of the CK722 is marked with a dot that indicates the collector terminal. And for one more time, here is the URL, the paper describing the curve tracer and its uses. We also, to automate the process of collecting data from these transistors, we've written a virtual instrument LabVIEW program that automates all of it. It animates the myDAQ, uses those resources that we saw earlier, the oscilloscope, and the function generator and the DC level control. And these are the actual measurements of the CK722 using this LabVIEW virtual instrument. We've swept the collector to emitter voltage from 0 volts to minus 10 volts. And the base currents were ranged from 0 microamperes to minus 75 microamperes in increments of minus 15 microamps. And the data were exported from that VI into Excel, because Excel makes very nice graphs that gives much better presentation than just a screenshot of the LabVIEW virtual instrument program. And now we can see label CK722 common emitter IV characteristics for each of the 6 rated values of base current. And I went ahead and calculated from these data the current gains of the CK722 under various operating conditions. This current gain, collector current to base current, is known as beta, and it's an important characteristic for accurate electrical modeling of the bipolar transistor for circuit simulation purposes with programs like SPICE or Multisim. And I've calculated it for each of the base currents from minus 15 to minus 75 microamps at 2 different values of collector to emitter voltage, minus 5 volts here and minus 10 volts. And the values we get are ranging from around just a little below 30 to, at the low end, 22.2. Now these values are actually quite low compared to modern transistors, where I would expect modern devices to have current gains of well over 100, maybe into several hundreds. But for the alloy transistors that was called technology of the 1950s, these are respectable numbers. Now, one thing I want you to notice here, you see that these curves have an upward tilt to them. Collector current versus collector to emitter voltage. And the slope of the curve gets more pronounced as you go to larger values of base current. This is a phenomenon that's called base width modulation, and it's characterized for a modeling of the bipolar transistor with a parameter that's called the early voltage, which was named for experimenter and engineer James M. Early. It's To find the early voltage, you draw tangent lines to each curve and extend them into where they cross the horizontal x-axis. And here is 0 milliamperes. So the x-axis is up here. We're looking at quadrant 3 with this particular presentation. In where these tangent lines cross the x-axis is the early voltage. Now the textbooks will tell you that these tangent lines should cross at the same place. In my experience in practice is they're close but not exact. So making an educated guess from the data that I've plotted here, I come up with an early voltage of about 40 volts for the CK722, which is actually a fairly respectable number practice for a PNP transistor. It's a parameter that's used in the SPICE model of the transistor, and an important one for accurate modeling of the device. So we also characterize another early transistor. This was a Sylvania ECG158 PNP germanium transistor. It was used in low voltage audio amplifier applications, typically battery operated. And the characteristic curves that you see plotted here with this LabVIEW VI are from a DC collector to emitter voltage from 0 to -10 volts for base currents ranging from 0 to -70 microamps in increments of -10 microamperes. The data you see here were exported to Excel and graphed to produce this family of curves. And I get a mean value of the current gain of about 110. The data sheet gave a typical value of 90 and an early voltage of around 42 volts. So, some parting remarks. The CK722 gave many hobbyists and amateur experimenters their first experience with transistors and solid-state electronics. Raytheon, to encourage this kind of experimentation, published a handbook of transistor circuits. 50 cents, cheap. Probably the greatest contribution that CK722 made in electronics was through the number of people that it introduced to solid-state electronics and drew them into the field of electronics through their experimentation. Anyway, thank you for visiting the early days of electronics for us, and join us for future presentations in this series. We appreciate your time.